Hi, Phil here again on our PD course. Today I'm going to go through some concepts of mathematical modelling. So be prepared to be dazzled. Here we go. So first of all, it belongs to the criterion that we use in Maths C, modelling and problem solving, as it does in Maths B and Maths A. I get a feeling that we do a lot in class of problem solving. We do lots of problem solving, but I'm not sure that we teach a lot of modelling. And so I'm going to talk about that today. So what does it mean? What does it mean? The syllabus tells us quite explicitly, I can't remember the page, but that it's any depiction, I'll read it for you, any depiction of a situation expressing the relationship between ideas in mathematical terms. And what do we mean by mathematical terms? Not just what we think in terms of modelling, in terms of finding an equation. So I think the types of models that we want to teach the kids are, and this is not an exclusive list, but the ones that are, in my mind, more typical would be teaching them about graphs, tables, equations, and diagrams. And I see them as equally important as each other. And I think the interweave of understanding between them is also something that's pretty important. So what I thought we'd do is have a look at an example of what we mean by modelling. So the one example I want to use is the Tower of Hanoi. And for those of you who aren't familiar with the Towers of Hanoi, what you've got to do is get a number of different size discs from one peg to across to a third peg, but the rules are you can't put down a bigger peg on top, a bigger disc on top of a small disc. And they're the basic rules, and what you've got to try and do is do that in the minimum number of moves. I think through me teaching maths, I think I've almost mastered this up to a certain number of discs, and after that I just think, why would I bother? But early on, there's a few little places that you can do this. Before I got computers, I used to make Towers of Hanoi in the manual art shop. Go crazy, the boys would let me make some and take them into class and let the kids play with them. But now that they've all got their own devices, probably better than what we've got, we can play that. And I just gave you an example on that last slide of what it looks like. And kids can manipulate using their digital devices and play the game. And I think it's good that they do play the game and get a sense of solving problems using some sorts of strategy. And the question is for towers, the Tower of Hanoi is what's the minimum number of moves that's required to move the disc from one end to the other? And I think you know the spanner in the works is for kids. And you say, well, what's the minimum number of moves you need to move 10 discs? Now that's a lot of moves. So you know one of the questions I'll be asking the kids is make it really not possible for them to do, particularly in a time frame. So then we'd have to sort of say, well, what strategies can we involve to solve the problem? So first of all, let's simplify it, and I think that first step is really important, simplify the problem. So what about if there was 2 discs? How would you do that? What's the minimum number of moves? Get the kids to do it. Then 3 discs, get them to move it. 4 discs. And then if you really need to, get 5 discs. And when we get that data, then we can say, well, let's extrapolate it so that we can say, what about for 10 discs? Now, quite obviously, if you said 5 discs was 31 and you asked the kiddies, what about for 10 discs? What do you think they're going to say for their answer? Obviously, 62. 63, apparently. And I'm sure afterwards Peter's going to tell me why they say 63. So there we go. So it's interesting how kiddies think in terms of how they create their models. So first thing we're going to do is once we've got that, we're going to create a graph, and that's what the graph looks like. And then what can we infer from the graph? That every time that we go from 2 discs to 3 discs to 4 discs to 5 discs, it almost looks like we're doubling the number of minimum, doubling the minimum number of moves. There we go, I can say it in English. And I think that's one thing that we can ask students to have a discussion about, let them play, let them investigate, and come up with the fact that maybe it is, looks like it's doubling each time. And in fact, what we then do is we can deduce that the pattern is that if m was the minimum number of moves and there was n discs there, in fact it is a doubling effect to a point. And in fact, if we can find out that m is equal to 2 to the power n take 1. Now, if we gave the kids Excel or using their graphics calculator and asked them to find out what that relationship was, I'm pretty sure that their regression line would come up would be an exponential function, which it should do, but it's going to give you with e as the base, which is not really the best thing for this particular problem. So there's another discussion you might want to have with the kiddies. What does e mean and what does the 2 mean, and have some sort of discussion there and come up with the idea that since it's doubling each time, then maybe 2 would be a better base to use. So if I now go back and say, well, now let's compare those two graphs, y equals 2 to the power x take 1, and the data, the raw data that I collected from playing the game, I can see they are in fact the same thing. Isn't that wonderful? So now I can use that model, the algebraic model, to extrapolate, and I find that if I was to use 10 discs, I would have to use a minimum of 1,023 moves. And so that's why we'd encourage the kids to find the model first rather than play the darn thing. And I'm sure that if it was me playing the game, I'd get to 999 and lose count and have to start again anyway. So I think we can use the maths there to encourage the kids to learn that process. Start simple, create some sort of some model. I think that doing it numerically first is a good thing, and then we can start looking at perceiving those patterns. All right, moving on. Sorry about the circle in there. It's the best I could do at short notice. Googly-izing pictures from the internet. I just made that word up. And we often, in structures and patterns, we ask the kids this particular nice little easy question here. If I go from A to B, and my rule is I can only move to the right or move upwards, I can't retrace any steps, how many possible routes are there from A to B? And again, we're going to use that same process to model that situation. So what I'm really sort of saying here through these examples is what process are we doing and what does modelling look like? So what I do, I might just simply, what about if A moved there instead, or what about if A was there, or what about if A was there? How many routes are there from those particular, let's say, nodes of a network? Maths kids wouldn't know what that meant, but that's all right. We can still introduce that terminology. But if I was to fill in all of those, and you can see here that if I fill in all of those numbers there, I get a beautiful little pattern there using Pascal's triangle, and maybe make that a little bit more obvious there. And so what I can start doing is looking at those patterns that when I'm doing the unit on structures and patterns, and I'm modelling using those that particular concept there. I can see this is a really good question here in terms of how can I use something that I already know to model this particular situation. How did we start it? Started simple, started developing patterns, and then how do we solve the problem? And in that way, it's a lot easier than asking the kids to do that than counting all 35 different pathways from A to B. Now, with all of this, we can say then that generally the act of asking kids to do modelling is quite a task. And if we look at the key points there that I've put on the slides there, some of you might be able to see there's a really nice link there between what I've asked you to look at before about key competencies and also CAPS, MAPS and CAGES, particularly when you look at some of the words like identifying assumptions, validity of a model, developing strategies to identify procedures. And I think that if we're asking students to model, what we're asking them to do is to get into a level of thinking beyond just the content, which I think is pretty important about what we do in our classes. I'm not saying it involves all the time, but it just may involve in different situations. If you want to stop the video and have a look back at those two examples and see which of those you can identify in doing that modelling that particular way, please do so and have a look. Great little exercise that you might want to do for yourselves. So if we were to look at why do we do it, students when we're working in classes, I think what doing the modelling here, that the students trust the technology that they've got. So when they get their little model, they're not really being able to validate their answer. Why would they draw a graph? Why would they draw a table when what they've got there is a simple answer on their calculator? And they're going to trust that till the cows come home. They're not going to look for errors. So what we're going to do when we're modelling there, we can while we're doing that, we can have a look at this these things that I've got there about analysing the effect of assumptions, etc., strengths and limitations of models. And I think that what we want to do is develop those in the students. What about as teachers? The challenges for us as teachers is that while we think that modelling is a really good way, what does that mean for our pedagogy in our classroom? If we want to teach the structures and patterns, Pascal's triangles, etc., what does it look like in our classroom if we're going to teach modelling as well? So there's a challenge for us as teachers. Guys,